This video I'm going to talk a little bit about attenuators, specifically low frequency, low bandwidth, high voltage attenuators that could be used with a multimeter. Started accumulating some low cost meters that I plan on evaluating. So far things are going as expected. All the meters I've tested so far have become damaged. You know, it's not uncommon for people to have low cost meters like these. I think in a lot of cases they do a fine job. I've said I've never spent more than $50 for a handheld meter. It's still true today. I was thinking about what you could do to make these more robust, and the obvious solution is to make an attenuator. That's not an uncommon thing to do. Take your resistor, put it in series with the meter. The meter's got a 10 meg input. Use a 990 meg and there's your 10x probe. No problem. Except if this resistor ever were to arc, it's going to feed all the energy straight into the meter. So you'd have to be very careful with this. The nice thing about this is that you can flip the polarity of the attenuator and it really doesn't matter from front to back. To get around the single point failure with a single resistor, we could have two resistors in series. If one arcs, the second one limits the current and maybe the meter gets saved. Another way is we could have two resistors with a divider in the center. And then we could have Zehners back to back to clamp the voltage at some point. The problem here is if this resistor were to short, obviously there's no fuse, all the current would go through these two Zehners and we'd probably still end up with damage here. The meter may be saved, but the attenuator probably would not be. If we put a fuse on both ends of the T attenuator, so we have a fuse, resistor, resistor, fuse, and now if this were to arc, we'll pop this fuse, or if this were to arc, we'll pop this fuse. This is called a balanced attenuator. It's nothing special. You've got four resistors now that make up the attenuator. The four outside ones are the same value, and then an inside one. Again, this could be flipped front to back, but it also can be flipped now top to bottom. You notice that we no longer have a low impedance path to the meter. So let's say I have a drawer full of 4.7 meg resistors, and I'll use that for the four outside resistors. And I'm looking for a 10-to-1 ratio. If I know this is 10 volts, for example, then I have a volt here. So it's 1 volt across 10, or 0.1. And I know that the current here is the same as the current through these two. So then I can calculate the voltage across R2 is 0.1 times 4.7 meg, or 0.47. Because it's dropped twice, if I want to calculate the voltage across R5, it's 2 times that voltage plus the 1 volt drop across the meter, which gives us 1.94. So to calculate the input current, we take Vn minus the voltage drop here that we just calculated, divided by the two input resistors. So that's 10 volts minus the 1.94 divided by the 9.4 gives us 0.85. So IN minus IRM, that I'll put to the meter here, is going to be the current through this R5. So the 0.8574 minus 0.1 through the meter gives us 0.75745. So the voltage across R5 divided by the current through IR5, or 1.94 divided by 0.757, gives us 2.56 meg. So that's the resistor that we would need for R5 to make this happy as a 10-to-1 attenuator. So what I would use would be like a 2.4 meg resistor in series with a pot. So if I wanted to look at the resistance to the input, I could then say take the 9.4 meg here and then add that to the equivalent resistance of this, and that would equal 11.66 meg. Fairly simple. This could be calculated for any type of attenuator that you'd want. Math is pretty straightforward. So if I build a circuit like that, easy enough to do. You can see here I've got my 4.7 meg resistors here, and my 2.4 is here, and I've got my pot here, no problem at all. So if I hook up a 10 volt source here, this is off of our precision reference, and I look at this with our low cost meter here. Again, this meter, it's about as accurate as it gets. I've never gone in and calibrated this, but yeah, this is actually hooked to a fluke calibrator, so yeah, it's 10 volts. We clip this onto our attenuator, and now we hook across the output of the attenuator, and we can see here it's 0.97 volts. So this gives us our 10-to-1 divide ratio. At least from a math calculation standpoint, this seems to work fine. You know, you could flip this thing any way you want. It doesn't really matter. If I flip in to out, you know, you're going to get the same values. There's no polarity to it. So that's one of the nice things. And again, because it is a high impedance input, for example, if I had this thing connected to our fuse input, it's not going to matter. The current is limited by the attenuator, so there's no way we're going to damage the meter at all by having the leads hooked up wrong. Likewise, if we switch it to ohms and we're putting out this voltage, again, it's not going to do anything to the meter. So what's the downside of this? Well, you can see here that the one thing that I've done is I've used these half-watt metal film resistors, and these particular parts are probably good for about 250 volts. So 250 volts in series here with another 250 volts-ish here. You know, this thing really for the input is not even going to be rated for a kilovolt. So if you're trying to measure high voltage, you can't be using these small film resistors. Now you could series a bunch of these up, okay, to increase the voltage. Of course, every resistor you add, you've got more solder joints, more possibility of a failure. So one thing here that's in this prototype I want to show you, this is a GDT, this is a gas discharge tube, and the reason that I'm showing that is if a transient were to come in here, so say I was measuring 1,000 volts, and we got a 10,000 volt spike, we don't want to pass that spike down to our meter. So this gas discharge tube will fire and short this out at the center here, and the voltage to the meter will essentially fall to 0 volts. So another problem with these is these resistors here are only rated for a half watt again, and if you run the numbers for this, you'd find out if we put, say, 5,000 volts DC into the front end, let's just say that was our target number, these resistors on the outside are going to dissipate 1 watt. So there's no way that these can handle that kind of power. The center one would be close, it'd be 0.4 watts. And we probably want some headroom here, so all these resistors need to be increased. So it's not just the voltage breakdown, it's also the wattage. Ohmite and Caddock both make resistors that are for high voltage. This is one of the packages from Caddock. You can see it's quite long. It's another package. This is also from Caddock. This is a Caddock as well. These are all 1% parts. This is an Ohmite here. This is a 1000 meg ohm resistor. You know, and the voltage ratings for these go up substantially as we're looking at high voltage resistors. This is an Ohmite as well. This is another Mach, a 9402. Again, rated for a lot higher voltage. You can see here the difference in the size of these two resistors. Pretty substantial. So really, you know, you have to decide how much you'd want to spend, get whatever accuracy you're looking for, and how much voltage you want to be able to handle, and what you need for an attenuation, and where you need to clamp your meter at. For example, Ohmite makes a part number SM 104034004FE. This is a 4 mega ohm resistor. It's 1.5 watts, 1%, and it's rated for 10 kV. That single resistor costs $3.68. Nice thing about it, at 4 meg, the input resistance then works out to 9.7 mega ohms. So it's fairly close to a 10 mega ohm input. And now we're talking about resistors that would be 10 kV in series with another 10 kV in series with our voltage across the center. So for a design like that to be able to handle much higher voltages, it's not an issue. So at 5 kV in, we're talking about again dissipating 1 watt. And those parts again are rated for 1.5 watts, so you've got some headroom there if you're only looking for 5 kilovolts. So something like that could be built. Another thing to keep in mind is the voltage of the probes that you're using or the leads. They may not be able to handle the rating that you're designing the attenuator for. Okay, so this attenuator here, well, it's kind of fun to play with, easy to build, no big deal. It's really, the meter is probably actually rated for more than what this attenuator is for. It may save a meter from a transient hit, but again, the attenuator itself is going to get damaged. So is this worth building? No, it's not. You really, if you're going to build something like this, you're going to have to build something a little better. Something like this may be more in order. We could put 4 fuses in each 4 corners. Now if we have a double arc across these 2 resistors, for example, and the GDTs fire and clamp, so we've got this flow of current through this way, we now have a fuse in each leg that will open up. It's critical which fuses are used. I use a type CC. These are a woven fiberglass. They're sand filled, high voltage. Fuses typically look like this one here. Some of these fuses will range up to about 30 bucks. We don't need anything real high current though, because the currents that we're talking about feeding through our attenuator are very low. In this particular attenuator, we're talking far less than 100 milliamps. One of the things you can do is DigiKey will sell you a pack of fluke fuses. You can see here these are rated for 440 milliamps. They're 1,000 volt, fast blow. Again, just a common fuse that you're going to find inside of a fluke meter. And because they're sold in these packs of 5, it's fairly reasonable. I'm not sure what I paid for these, but I think it's like around 20 bucks for the 5. You could easily end up spending 20 bucks for a single fuse. So it just it depends what you want to spend. The nice thing about an attenuator like this is, if these fuses blow, something's arced here. These resistors, I wouldn't trust them after that. So I look at a circuit like this as disposable. In this case here, I'm balancing 2 10 mega ohm resistors across to 12 meg and back to the 10 megs. If we look at this as a T attenuator, you can think of it as a 20 and a 12 and another 20, and this gets us our 10x. So the 20s are made of the 2 10s, the 12 in the center is made of the 30, and the 2 10s this way. The reason I've separated out the 2 10s is this resistance causes these gas discharge tubes, which are in series, to actually charge at the same rate. So when this fires due to a transient, these actually share the voltage across them and they'll kick at roughly the same point. Now I'm using a Caddock part in MX431 series. This is a 2 watt part and it's rated for 7,500 volts. So that's these parts here in series. So just from the 2 here, you're looking at over 1,500 volts before this thing is going to break down. Again, there's no polarity. It's high impedance path to the meter. A short or an open on any component in this circuit is not going to cause the voltage at the meter to exceed 1 kV. If they're 2 fault, again like these 2 resistors for example, then we have these fuse protection. The one I would build would be potted, so it would be watertight, and mechanically I would design this for a minimum of 8mm spacing. So this is the completed attenuator here. Again, there's no polarity front to back, it's just like what I showed. This is actually pretty heavy. It's completely potted. If I took this off, all you're going to do is see a lot of gray. It's a rubberized potting compound. You can see it's got the double insulation connectors. It's a non-serviceable device. So if any fuse ever were to pop with this, again, I would just throw this device out and start over. Cost to build this thing, again, it depends what you're looking for. This particular one, about $150 in parts here. You know, the resistors. This particular one is actually quite expensive. It's about $100 in components. You know, and it's really going to come down to your personal choices that you're going to make if you need something like this. What do you need it to do? What do you need it to hold up to? And again, for this meter, what I did is I bought some extension cables and a set of probes for this. So we just plug our probes in the one side and the meter to the other, and there you have it. And again, this would provide additional protection for this meter. These probes are Cat 3 rated. There's some extensions. I did another video where I showed these. They're a fairly nice probe. I personally would have no concern about taking this box up to several kV. I mean, it's designed for this. I have more than adequate spacing in all the components. I actually have a Teflon that I've machined out for the to hold all the parts, and there's Teflon spacers that run between the components. There's at least 10mm of spacing between all the parts, and then additionally it's potted. So this this box is rated for way higher voltage than what the probes here are rated for. Frequency response wise, this isn't going to do very well. I was targeting, again, just to use this with the meter, so you know, 400 Hertz would be adequate. Potting compound hasn't quite cured with this. It's got about another 12 hours. Prior to it being potted, the bandwidth of this was about 1 kilohertz, and I don't think the potting compound is really going to affect this. So that's more than adequate for me to use with the meter for measuring high voltages. And again, nice thing here is if I were to have this plugged into a current input or had it in ohms, it really doesn't matter. This is going to limit the amount of power going back to the meter and should prevent any damage to it. Again, I've designed this attenuator to work with meters. I have a 10 mega ohm input. That's pretty common. So for my use, that's going to work fine. Again, this is our transient generator. If you were to zap yourself with this, yeah, you wouldn't want to do that. So normally if I were to connect this up to a meter like this, this meter here has no protection. It would probably just blow. Running it through this, probably not a problem at all. I'm not going to use the safety cables. I'm actually going to use these BNCs here. Now I'm going to set the meter up here for volts. Set on 20 volts. And I'm just going to turn on our generator here. Okay, so generator is now charged up and it's starting to fire, and you can see the meter here responding. Yeah, I run it in ohms, no effect at all. As a matter of fact, the energy on this is so low, I'm gonna put my fingers across this here. See, and I can't even feel that. That's how low the energy is. Or if you're looking for a way to protect your meter, this may be an option for you. Again, it's pretty common practice for a few of you. Hopefully this video's been helpful for a few of you. I know, again, myself, I plan on using this thing in the future. I build attenuators like this myself, on and off, and I'll typically do it with 2 resistors just to set up a divider. So this will be nice to have. It's a lot more permanent, and it's able to handle a lot more voltage than what I would normally have done. So cleaner setup. So this will be a good addition for my home lab.